let's discuss about stress and strain relationship. Okay, in the sense, say you have an object and you're going to have weights on the object, correct? And the body is going to extend, correct? Let's talk about a simple example of a spring. Okay, now if you look at this, see, you have an object here, as in like one particular stand kind of thing, and here you have a spring, and the spring is connected to one particular weight. Okay, you have a weight which is connected to the spring. Now what happens once you connect a weight? The spring is going to extend, correct? Now let's say you're going to add one more weight to it. So the extension is going to increase, isn't it? Instead of this, you're going to see another image where you will going to have an extended spring. You can say that the same spring. So this is the extended spring, correct? Now what is the stress with what is applied on the body, and what is the strain which is developed by the body? Now here, and can I add any amount of weight for this particular spring? Will it come back to its original position? Or is there any point where the spring is going to break? Okay, or is there any point where it's going to get permanently deformed? Now we are going to look at these kind of things. Okay, now this is the most important video because we are going to talk about stress and strain relationship. Alright, let's start with this particular derivation. It's more of explanation and conclusion types. For this, the main thing what you have is a graph. Okay, so if you're going to look at this, see, this is the stress strain graph. Okay, if you look at the x-axis, you have strain, and if you look at the y-axis, you have stress. Correct? You have the stress and strain graph. You are going to find a relation between, if you apply a stress, how the body is going to get strained. Okay? Now there are certain points. If you look at it, you have A, B, C, D, E, F. Correct? And if you look at, there are certain regions, like you have OA is one of the regions, AB is one of the region, BC, CD, like this you have different regions. Correct? Now we'll have to discuss in detail what these points represent and what are these regions. Okay? Now let's start with point A. Okay, now the first is point O. If you look at point O, there is no stress, there is no strain. Correct? Now point A is called as the point of proportional limit. So we are looking at point A here. Correct? This is called as point of proportional limit. In the sense what? If you look at the region OA, so what you are looking at is you are going to look at this particular region. Okay, now if you look at OA, OA is going to be a straight line. Since OA is a straight line, this obeys Hooke's law. Okay, Hooke's law is what? Stress is directly proportional to strain, correct? So since it is directly proportional, OA, this is going to be a straight line. That means Hooke's law, this is very important. Hooke's law is obeyed in this particular region. Alright, that's why A is called as point of proportional limit. Alright, let's move on to the next point. The next point is point B. If you look at this, this is point B, correct? Now point B is called what? It is the point of elastic limit. This is the elastic limit. See, elastic limit in the sense what? Now here from O to B, if you look at this entire region O to B, this is what we call as elastic region. Okay, the body is still elastic here, in the sense it can still come back to its original position. Alright, so it is still the elastic region. Now if you look at the region AB, See, AB is not a straight line. Correct? AB is not a straight line. In the sense, Hooke's law is not obeyed in the region AB. So what you can say is, Hooke's law is not obeyed. Hooke's law is not obeyed. And which region are we talking about? We are talking about the region AB. This is the region where it is not, okay, it is not at all obeyed, but still B is called as the point of elastic limit. Understood? So this is a very, very important point of elastic limit. And the region what you are looking at is region AB. Alright, now let's go for the next point, which is point C. Okay, let's go for the next point. Now point C, this is a very, very important point, because look at the graph here. Now if you look at point C, it is on a particular higher level compared to B, correct? Now if you look at point from B to C, if you look at this region BC, it is one non-linear, correct? And also if you look at the stress and the strain graph here, see what's happening? Strain is increasing much more compared to that of stress, correct? Like in the sense, see if you draw a line from B to down here, and if you look at from C to down here, okay, now if you look at the other part also, that is, from stress to strain, if you look at the, the relation here, strain is going to increase more compared to that of stress. Okay, and obviously BC region what you are looking at, this is non-linear. It's a non-linear region, correct? Now what we are looking at is C is called as the yield point. Okay, now yield point in the sense what? See here, the wire or whatever that spring you are going to talk about, it is permanently deformed. Okay, anything which crosses the elastic limit is going to set permanently. Okay, there is a permanent set in the particular wire or the spring or whatever you are going to take. Alright, now here what we have is something called as the plastic deformation. Okay, again I'll repeat, this is called as plastic deformation. Alright, now why we mean by plastic deformation? The reason is here at from B to C, beyond B, that is once you cross the elastic limit, in that region BC, you are going to have permanent set. Okay, there is a permanent set in the structure of the body. That's why C is called as the yield point. So this point C is what we call as yield point. And here very clearly Hooke's law is going to fail. Okay, Hooke's law, this part of the curve what you're looking at, that is from B to C, this part there is no obeying of Hooke's law. Understood? So this point C is what we call as the yield point. Okay, now let's go for the next point, which is point D. Okay, now we have to come to point D, correct? Now if you have to come to point D, that means the region what you are looking at is region CD, correct? Now the CD region is a very, very important region. Now look at this particular region CD. It's almost a straight line. There is a small dip. If you look at the graph very carefully, from C to D, the graph goes a little down. It's not much of a steep. Okay, it's not a very steep downward curve, but there is a small dip in the curve. Now what we are looking at, if it is going from C to D, now look at the stress and the strain. The strain is increasing a lot because you're going from point C to point D, isn't it? This is the strain what we are looking at. And if you look at the stress, there is barely any change in the stress, correct? Now the strain is, there is no much change in the strain, but there is a lot of change in the stress, correct? Now that means what we have is that from the yield point, that is from C, where the wire or the spring or whatever object you have, it yields to the applied force, the external applied force. Okay, it just gives up, it yields to it. Okay, so this CD region, whatever we have, so this is the yield region. In the sense, this is beyond the yield point, correct? Now what you have is that the corresponding stress, from here, from C to D, this corresponding stress what you have, that is what we call as yield strength of the body. Okay, this is called as yield strength of the wire. Now here, up to point D, see, till this particular point, what you have is you're going to have a perfect plastic condition. Okay, let me repeat this again. From C to D, you are going to have perfect plastic condition. Okay, now this is a very important point, because from O to B, you had elastic. Till point D, you are going to have perfect plastic condition. Alright, the next part of it is point E, correct? In point E, now look at the graph. E is at the highest position in the graph, correct? The maximum, or you can say it's the ultimate, correct? Now what we are looking at is, we are looking at this region D, E, F. We are looking at this entire region. We are not just looking at one point here, we are looking at the entire region. Okay, now see, this point E is the ultimate point, in the sense you are going to have the maximum the wire can withstand. Okay, now till point D, it was plastic. After that, if you look at DE, even there is a stress here. See, this entire thing, whatever you are talking about in the x-axis, this is stress, and this is the corresponding strain for the body, correct? You have stress and strain. That means we are adding couple of more and more weights to the body, in the sense for that particular wire or the spring, correct? Once it reaches point E, okay, once it reaches point E, now what you have is the ultimate stress the body can take. Okay, the ultimate stress the material can take. Okay, this is what we mean by that DE region. Now after that, if you look at DEF region, okay, now EF region is, even if the wire is unloaded, a little bit, okay, from point E to F, we are looking at point E to F, this region. So here, even if you unload a little bit of weights from that extended spring, so what's going to happen? The wire will start to thin. The wire will start to thin because of the expansion. Okay, there's a lot of strain and stress on the body. It is going to start expanding. It expands so much that at point F, it can no longer hold it. Okay, so point F is what we call as breaking point. Okay, this is called as breaking point. Alright, now remember, point E is the ultimate stress what the body can take, correct? Or you can also call it as the breaking stress. So this is the breaking stress. Anything beyond this, the body cannot sustain anything. Okay, the body, the wire or the spring is going to start thinning, and as it thins out, then because of that expansion, the spring is going to cut, and that point is point F. Okay, so remember this portion DEF, what you are looking at here, see this point DEF region here, this DEF region, this shows the plastic behavior of the wire or plastic behavior of the spring. Understood? So O to B, whatever you have is the elastic region, correct? Then after B, so what you have from C to D, that is the yielding region, correct? There also it's going to behave like plastic itself. Then from D to F, it's going to behave like a plastic material. Understood? Now, if you see the x-axis, there is something called as O dash. Now, O dash, this distance, whatever you are looking at, this is what we mean by permanent set. If you look at this, it's a permanent set. Permanent set in the sense, see, the body is already deformed. It can no longer go back to its original position. So the body is already set. The wire is already extended. It cannot go back to its original position. Understood? That's why we call it as a permanent set. Remember, I was talking that in point C, in that C to D region, point C, the yielding point, you are going to have a permanent set. Correct? Now, if you look at this particular graph, okay, every point has a particular region, and every region is going to tell you certain one or the other properties as to how a spring or a wire behaves when a load is given to it. Okay, elastic region, plastic region, and you have the different points are there. Okay, one is the proportional limit, one is the elastic limit, yield point, and then you are going to have ultimate stress, and finally the breaking point. Alright, this is the relation between stress and strain whenever you have a spring or a wire and you're giving load to that particular body.